Weiss. If you're just watching this video, I'm going to start it just a minute early, and I'll be waiting for folks to join us on here the 29th of April for our 9D chemistry class. So in just a minute, folks will be joining us. Our topic today is catalysts. So we're going to be thinking about what these are and doing a couple examples on the board together. I'll just wait for folks to join me, and there's somebody already. So as soon as you're here, go ahead and say hello so I know you're around. Dynamite. Okay, so I've got Ada is here. I'm guessing this is Victoria. No, message retracted. Okay, let me know if you're here. Carlotta's here. Got some others that have joined up, so let me know. Aaron is here. Good morning, you three. Let's see who else I got coming in. We'll get going as soon as I get a few more here. There's another one or two. Macy, good morning. And others are joining, so tell me who you are. Hope everybody's well. And yeah, keeping your sanity at home, trying to stay busy, but not too busy. There's Victoria. Good, I see others joining me, and I got Freedy. Good morning, Freedy. Dynamite, and a couple others as well, so let me know who you are. Tell you what, while we're waiting for everybody, let's just warm up our brains a little bit. So here's a question, and that is, what do molecules have to do to react? There's more than one answer. What do molecules have to do to react? See if you know from last time. And everybody else just joining us, please sign in so I know you're here. Carlotta says collide. That's good. And what else has to happen? Maybe somebody else has a different answer. Collide is true. Freedy writes touch, more than touch. Let's say collide. So it involves really hitting. Macy says that too. Good. Something else has to happen during that collision. Let's see if you find it in your notes. Carlotta says there has to be a lot of force. She's right. And force to do what during the collision? Colliding on the right side, says Aaron. That's good. So in other words, sometimes they collide on a side that doesn't help, and they need to be right on the correct side to do what? And that is, yes, Carlotta, they have to break apart. So really, to react, we're talking about breaking bonds before they make new bonds. And to do that, they have to collide with a lot of force. You got it. So they need, yeah, Victoria, they need enough energy to hit, and that energy then is used to break the bond. Okay, then they can make new bonds. Okay, I got 9 of you. So far I got Aaron, Ada, Freedy, Macy, Carlotta, and Victoria, but I think there's a couple more. Oh, there's another one. So Isabel says hello. That's good. Anybody else want to say hello before we start up I had so many last week. I wonder where everyone is this morning, but maybe you know better than I. But we're going to start up. They'll just have to watch the video. Okay, let's go ahead and begin. So right now we're talking about our goal for today is this, and I got some new markers, so I hope you can see better today. It's what are catalysts? Just as a reminder, last time we talked about 3 ways to increase the rate of a chemical reaction. Um, well, let me ask you, what were the first 2? 3 ways to increase the rate of a chemical reaction. You can either, and then the third one we'll do today, that's catalyst. So you got 2 for me, 2 ways to increase the rate of a chemical reaction. You got at least one you could write down. That would be swell. Victoria writes, increase the temperature. Exactly right. Then they hit harder and more often, and we get more collisions and more old molecules break apart. Good. Increasing temperature. And I've got another one from, Freedy, that would do it as well, increasing their speed. Yep, that's right. Um, and Aaron writes in, add more particles. Right, as does Victoria. So that's right. So adding more particles, they're more crowded, they collide more, and there's more chances of collisions. Yeah, and they can then react. Okay, yeah. So what are catalysts? Catalysts are well, let's write a couple things. So grab some paper. I'm going to have you take some notes here from my whiteboard. Okay, so what are catalysts? Okay, catalyst, and in German it's really similar, Katalysator. Okay, you might have heard of that word with cars, but we'll come back to that. These are molecules that speed up reactions, RxN for reaction, without being used up. In the process. Okay, if you're writing, let me read that off the board to you and lean back a little bit so you can see. So it says, what are catalysts? Molecules that speed up reactions without being used up in the process. So in other words, you can use them over and over and over. You don't have to keep adding new ones. They don't get used up. What else I want to tell you about that before we start? They provide an easier way to react. Easier. So in other words, if they're present, instead of having to have this much force, boom, maybe 2 molecules can react with this much force, boom, and still break apart and get the reaction started. You know what I'm saying? Okay. Right. Anybody else joined us? No. I guess I got everybody. 1, 2, 3, 4, 5, 6, 7. No, I've got 9 people listed, but maybe I had a couple people in the wrong spot. All right. Say hi if I haven't talked to you yet. Okay, so I know you're here. You can get the participation points. Ute. Good. There's 2 types of catalyst, okay? That's what we're going to talk about now. Each type has 2 different names just to make it more confusing, all right? The first type is called, let's see, what do I want to do first? I want to do the heterogeneous. Heterogeneous. While I'm writing the word hetero, maybe someone can tell me what hetero means as a prefix, hetero. Okay, so heterogeneous. The other name for them is contact catalyst. So heterogeneous or contact catalyst. Hetero, anybody got it? What that means? Not the same. Yeah, Isabel, good. So it means different. It means different. So if it's hetero, it's something different. So what that means, so hetero means, you ready? It's a different chemical phase than what it works on. You know, the phase is solid, liquid, gas. So if I'm chemical and I'm a liquid, maybe you're a gas if you're the catalyst. Or if I'm a chemical and I'm the like in solution, maybe you're a solid. So it's just a different phase. So hetero means is a different phase as the reaction chemicals. Okay. Yeah. So different phase as the reaction chemicals. Good. Let's go ahead and draw a little picture and talk about our main example today. And that would be, well, let me ask you, have you heard the German word Katalysator? And if so, where is one found? Katalysator. Rhea Tuber's here. She couldn't chat for some reason. Well, glad you're here, Rhea. Feel free to chat now and answer my question. So, where would you find a katalysator? Anybody know? I bet you've heard the word before if you've been here in Germany a while, which most of you have. I'll give you another little bit to guess. Okay. In English, we call it a catalytic converter, and it's in the exhaust system of a car. So here we go. So we're going to do this as an example. Catalytic converters, or I'll just make it singular, in car exhaust. Okay, catalytic converter in car exhaust. Cars, yes. All right, Carlotta got there. Okay. Let's see what this does. Exhaust is, Auspuff, so that's the stuff coming out of the back of the car. Well, imagine you got a long tube, okay? And in this tube, that's where your exhaust is coming out. But before it comes out, it goes through something that's pretty cool. It goes through this like a grid, okay, like a gauze. And as it goes through this gauze, I'll make it like a grid here. As it goes through this, it gets cleaned, and we're going to see how that is, okay? The important thing is this gauze is sprayed with a really expensive metal. So what's the most expensive metal you can think of? That's what they spray this gauze with. By the way, the catalytic converter, because of this metal, is the most expensive part of the car. So I'm looking for an expensive metal. Let's see some guesses here. Punch something in. An expensive metal. And I got another person joined us. Let me know who you are. Whoa, Ray is already there, and so is Freedy. Platinum is correct. So the symbol for platinum is PT. So I'm going to write PT coated. PT for platinum, okay? Okay, now, here's the deal. Well, that's kind of in the shiny spot. I hope you can see it. Yeah, it's even more worse. All right, well, we'll draw some more here. At any rate, here's what's coming in, right? Turns out, as teachers often do, I lied to you. I did not tell you the whole truth. I told you that when hydrocarbons burn, combustion, they make the two things and. So I told you that when hydrocarbons burn, what two things form? When hydrocarbons burn, what have we learned? What two things form? Can you punch out an answer for me? Water, Carlotta, that's one thing. Good. And that's not a problem environmentally, so that's okay. The other thing that forms, not salt, no. No, you're thinking of when I add acid to base. That's not acid to base. When I burn something, right? When I burn something. No, a salt doesn't form. No, 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 no. I'm burning something like gasoline. Hint, hint, hint. So no, 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 no. Come on. Let's make some better guesses. You did a lot of equations for me like this. I burn any hydrocarbon. I get two things, water and what? Not a salt. Hey, Aaron's got it. CO2, right? Carbon dioxide. When we burn coal, gasoline, oil, natural gas in the kitchen, right? All of that gives off CO2. Okay, turns out that's mostly what happens when I burn coal, oil, gasoline, but not entirely. Turns out I still get a little bit of bad stuff that comes off. I know CO2 is not good anyway, but what's even more worse is CO, carbon monoxide, because it gets in your lungs and it's a poison. So here comes a bad boy. So part of this exhaust is CO. And another part of the exhaust is a part that makes smog. You know that brown look to smog in the summertime that we don't have right now because of Corona, but like Beijing has all the time, is from the chemical NO2, nitrogen dioxide. That makes smog brown. So these two bad boys, we get some of both of them, CO2 and NO2, as fuels burn, especially nitrogen is just a byproduct of burning fuels. And that's not good. So we want to get rid of it. So what happens is, and now we're going to take a close look right here. So here we go. I'm going to do this over here. So let's take a close up look. Ready? All right. So here's what happens. Here's the wire. And we learned that metals, Carlotta asks, how does carbon monoxide exist if it's not balanced? You can balance it. You can say gasoline plus O2 makes CO plus water, and you'll still be able to balance the thing. So that can still happen. At any rate, let's say the CO comes out here. Let's do the CO first, carbon monoxide. Turns out C and O are both nonmetals, and nonmetals both want something. What do nonmetals tend to want to get more of? Think of where they're at on the periodic table. Nonmetals want to get more what? It's going to be true of nitrogen as well. So N, C, and O want more. Hint, to fill up their shells. Electrons. Good. A couple of you got. So they want more electrons. Okay, so here we go. So far, I got NO2 and CO are coming to hit this screen. This is a screen with a platinum coating. So now I'm making a little inset here over to the side. And I think that is going to be easier to see if I draw it over here. Okay, so here comes the CO, and the CO says, ooh, look, platinum. Platinum is on, this stuff is coated with platinum. So the platinum is this coating. So here comes the CO, and the CO says, wow, platinum's a metal. It's got electrons, free moving electrons. Right, Otto says the same thing. Good. So the CO is very attracted to these electrons. So the CO lands on this, and here we go. And C and O, just for a moment, are kind of both looking down. You know what I mean? Like they're looking at that platinum. And what happens is that makes the bond in between these guys weaker. So here's the little bond in between. I'm not going to draw it, but that bond you'll have to imagine between the C and the O. And what happens is somebody else comes flying in. You ready? Just by luck, what comes in to hit them is an O2 molecule. Slam, bam, boom. And we get a collision. The C and O break apart and rearrange, and the O2 breaks apart. And one of the things that comes off is CO2. CO2 is not a poison for human beings, so it's good that it comes off. It's not great for the world, but it's better than you and I breathing carbon monoxide gas. Okay. So what I'm getting at is this platinum essentially lures these guys in and says, hey, look at these electrons, come on in. And then it doesn't give up the electrons, but before these guys can do anything, the O2 slams into them and changes the reaction, becomes CO2. Yes, there's an extra O, but that gets taken care of because there's so many of these reactions happening. The other one that does this, of course, is NO2. So here's an NO2 landing. It lands on the platinum as well, again, attracted to the electrons that platinum has. Okay, and again, O2 slams into this guy, shabam. This time what happens is they break apart totally. And it happens with several of them at the same time, so I end up getting nitrogen gas, N2. Yes, I know it's not balanced, okay? Yeah, there are other ends where the same thing happens over and over and over. So there's enough that I get N2 out of it, which you're breathing right now. It's also not poisonous. So what I'm saying is the catalyst is the platinum, okay? And so the platinum can be used up. The platinum can be used over and over and over. Okay, so if you want to add this to your cartoon over here, so the platinum coating, and out comes my two things that are less dangerous, N2 and CO2. By law, in Germany and the US and many countries, you have to have a catalytic converter on the car. Before this was the case, streets were a lot stinkier back in the 40s and 50s and a lot more polluted and a lot worse for people's health, to be really blunt. These are 300 euros or so, the catalytic converters. What they do is just the sprayed platinum is super expensive. If you have a junk car and give it to a junkyard, the first thing they'll do is they'll take the catalytic converter out and sell the platinum back to the company. It's not much, but yeah. And Carlotta has a good question. Does this filter have to be cleaned? No, that's the cool thing about it. The platinum can be used over and over. It doesn't get plugged up. The COs and the NO2s land on the platinum, bam, spam, bam, get hit by O2s, and then convert to CO2 and N2, and the platinum can be used over and over and over. Oh, and look, that was in our definition of catalyst. They can speed up a reaction without being used up in the process. So, hey, I don't know where to put it. You're going to have more room on your paper than me. I'm going to write it up here. Hey, the PT, the platinum, can be used over and over. I'll just say can be reused. Kind of cool, huh? So now you know something about your cars and you know something about the exhaust coming out the back. The catalytic converter is not 100%. There's still a little bit of carbon monoxide and NO2 coming out the back, but not nearly as much as there would be without the catalytic converter. Good. Before I erase my little tiny whiteboard that I just ordered, do you like it? Nice. So before I erase that and start all over, I want to see if you got questions and give you a chance to catch up and write your notes a little bit. So any other questions on a catalytic converter? We're going to do the other type of catalyst in just a moment. But that's the first type. Oh, by the way, it's heterogeneous, right? Because the platinum is a solid and the other two are what phases? So right here, the solid platinum. So heterogeneous, there are two different phases. So the platinum's a solid, and Aaron, thank you. The other two, the carbon monoxide and NO2, are gases. So they're different phase. Hetero means different. So it's a heterogeneous catalyst. The other name is contact catalyst. And that makes sense, right? Because here comes the CO. Oh, it comes in contact with the platinum. Okay? When it goes on this little grid here. And let's see if I can lift that for a sec so you can see that grid. It's just, all right, it just looks like that. It's just a grid. Okay? I hope this doesn't fall over. It's pretty rickety. Okay, then let's do our second type of catalyst, okay? How are we doing on time? We're doing okay. All right. Things are a little tight here, so I'm going to stand up and erase this. Might be a little more effective. Look at that. I brought a brand new eraser from Amazon. I'm just all set for you guys. Now, the word catalyst is also used in your English class. So if you want to impress your English teacher, you can tell them, I'm a catalyst for change. Now, that's a political word, right? For those that are into politics or into like MUN, a catalyst is somebody who's really active, who really helps do things and get things started. Right? Just like a chemical reaction. So you can be a catalyst for change. That's how it's used in the English language. Okay, cool, huh? So English, chemistry, all related. Good. Let's do our second type of catalyst. Here we go. So the second type, well, if it's not homogeneous, guess I just said it, sorry. Okay, if it's not heterogeneous, it's going to be, you guessed it, a homogeneous catalyst. Homogeneous. And the nickname for that is carrier catalyst. Homogeneous carrier catalyst. So it's the same phase as what it works on. That's why it's homogeneous. Okay. And by the way, it looks like another person joined us. If you haven't said hello, say hi so I know who you are. Homogeneous, same phase, and it's carried along like a suitcase, okay, by the reaction. So same phase as the as the reactants that's working on. Remember, we got reactants and products. Isn't it spelled homogeneous? Did I misspell it, Anna? Homogeneous. I think I spelled it right. That probably looks like a C to you. Homogeneous. It's supposed to be an E. Yeah, that's how it's spelled. So you spelled it right also, Anna. Okay, so same phase as the reactants. Man, time flies while you're having fun. Okay, here we go. Let's do our example before we get out of here. The example involves a chemical you're going to study next year. Oh, I got it. Okay, I follow you. Chemicals you're going to study next year include organic acids. So the example is breaking down formic acid. But I'm going to give you the German name for formic acid because it's fun. All right. So it's, well, I should have capitalized it. Sorry. Ameisensäure. So guess where it's found? Ameisensäure, probably found in some of you are fast. Right, Freedy, in ants. Okay, not uncles. No. If you ever been bitten by an ant and it hurt, it's because they bite you and give you some formic acid. Not so nice, huh? All right, well, just the way they are. So here we go. You might say, well, why are we talking about breaking down formic acid? Well, you're going to find out. So stay with me. Okay, here we go. Here's formic acid. It's got a C and a double bond O. No, I want to put that over here. Hold on. C double bond O, an H, and an OH. And what happens is, to break it down, I gotta break it down into water, but to break it down, the OH here and the H are not really all that close. So here comes your catalyst to help out. You ready? Your catalyst slams into this sucker. Shaboom! The catalyst is an H plus. Ooh, Carlotta, is this the catalyst in an enzyme reaction? Could be, depending on where it is. If it's in the human body, we could call it an enzyme. We'll come back to that. Thank you, Carlotta. My catalyst this time is a lowly H plus. Okay, from earlier this year, what sorts of chemicals give off an H plus? Ooh, everybody be able to say that really quick. What sorts of chemicals give off an H plus? Nice. Got one answer already. See if some others have it as well. I'll change pens for grins. Oh, several do, including Ada. Thank you. And Macy. Nice. Okay, so this could be from any old acid at all. So it's easy. And these are both aqueous, okay? Both aqueous. AQ. They're both in watery solutions, okay? We'll see where it is, okay? So what happens is this goes slam-o-bam, and it joins on briefly. The H plus joins the formic acid briefly like this. I'm going to show it to you. This part's the same. And I got an O, and I got an H, and I got another H. And you know what? That makes this whole thing plus, by the way. Well, that's really unstable because normally, oxygen only wants what? there's two bonds, right? Here it's got three. It ain't going to stay that way, so I'm going to keep going. So what happens is this sucker comes off and I get water, boom, good old H2O. And this becomes a double bond here, and I get CO2. So it breaks down into CO2. That's a gas, by the way. Water is a liquid. And check this out. I got an extra what coming off? An extra H plus. Well, and that is aqueous, by the way. Hey, look at that. So notice, interestingly enough, it's not the same H plus that comes off. A different one comes off, but it doesn't matter. I start with 1H plus. I end the day with 1H plus. Life is good. Therefore, we say H plus is the catalyst. It makes this reaction happen in an easier way. So instead of two molecules of formic acid having to really hit hard, if they get hit by an H plus and it joins and then it breaks the thing apart, it can do so with a lot less energy. And we'll see what that means when we talk about diagrams next hour, next week when I see you. Okay? Yud, how we doing? We're doing okay. I'm pleased. Okay. That's the main thing we wanted to do anyway. So now we can talk about the fun stuff. Ready? Okay, so where does this happen? Where is this reaction found? Okay, well, you probably know I'm from Montana, and I worked for many years as a ranger in national parks. And one of the things I used to see in Glacier National Park in Montana were bears, grizzly bears and black bears, and especially black bears. Once in a while, you'd see evidence of this, and one time I saw it too. Black bears love to eat ants. So here I'm a black bear. Come up and here's a big mound, an ant mound, right? So here's what they do: they take their paws and they beat that ant mound and spread it all around, and they get the ants really upset. And then they put their paw down on the rest of the ant mound, and the ants crawl all over the paw. And of course, they got a lot of fur, so they're not going to get hurt by the formic acid. And the bears lift up their paw and they lick off all the ants, and they eat the ants. So bears seem to like ants, especially black bears, I've noticed. And what's interesting is biologists have kind of checked it out. They don't really get a lot of nutrition from this, okay? It's not like a piece of bread or something. But apparently they like the flavor because it tastes sour. You know, we like some things that are sour. Apparently bears do too. They like ants, okay? They like amyloids, a formic acid. So interestingly enough, then, go back to the reaction. Ready? Here's the formic acid eaten by the bear. Where's the H plus coming from then? Where's the H plus coming from in this situation? Where's the H plus coming from in this situation? So again, bear eats the ants. Where's the H plus coming from? Don't make it hard. Carlotta's right. The bear. Where in the bear? Somebody else. Where in the bear is this coming from? Freedy says water. No, it's not water that they're drinking. No, something much easier. Where in the bear? The paw. No. Mouth. No. Hint, you've got H plus in this same part of your body. No, it's not. It's not in the mouth. Where's this H plus coming from? Ooh, I got you on this. I thought you'd be quicker. Oh, one person's got it. I'll give you a hint for everybody else. HCl. Yeah, it's Molly's here. Why didn't you say hi, Molly? Ms. Lucas. Okay, Molly, you're right. It's stomach acid. Okay, and a lot of you got it now. So it's from the stomach acid of the bear. Okay, so the bear has HCl and H pluses come off, and they make the formic acid break down easier. But you know what? If things get really tough, one starvation food for human beings is ants. So if you're out in the woods and something terrible happens and you're hungry, you can actually also eat ants and you can get some good out of them. You can break down their formic acid, and it's not like the best food, but it is edible for humans too. How about that? Yeah. Though if you eat too many, maybe you'll need some ant acid. Sorry. Okay. Okay. Anybody there that I haven't talked to yet? All right, that's how catalysts work. Then, and if you're listening earlier or writing or reading earlier, you might have noticed Carlotta already mentioned this. I want somebody else, not Carlotta, to answer this. Okay, where's the reaction found? Well, we can answer that in the bear's stomach or in your stomach if you eat some ants. They're sour. If you like sour things. Okay, so here's my question now. What are Yeah, you could read that. What are enzymes? Hint, biology. What are enzymes? Enzymes. You use them all the time, by the way. Waiting for a response. Something for digestion. Yes. Some of them, Freedy, are used for digestion. Good. You're red hot. Anything else we can add to that? They're chemicals. You got it. They're red. Well, you're even more warm now. So they're chemicals. Some are used for digestion. Some are used for other jobs in the body. They involve proteins, Victoria, yes. They are, Rhea's got it. They're catalysts formed in the body. So the most important chemical factory on the planet is you. You make tens of thousands of different catalysts in your body. You know that? Isn't that cool? So these are, and so do other animals and plants too, okay? Enzymes are biological catalysts. Let's list one example that Freedy alluded to. What's the catalyst or the enzyme that's used for digestion? Did you learn that one this year, maybe? We still got another couple minutes. So for digestion, any enzyme you can remember. Starts with an A. If you eat a cracker, then this enzyme is formed in your mouth. It's called, any other guesses? Amylase. Maylase. A lot of enzymes, by the way, end in ASE, but you'll learn that if you take like Lystone's Bio or something like that. Okay, the other one is one that is made to process sugar. And if you're a diabetic, if you got anybody in your family who's a diabetic, they have to take shots of this. What do they take shots of, diabetics? What are they missing? They need more what stuff? Freedy, nice. He's awake today. Yeah, they need more insulin. Insulin. Yeah, good. Exactly. A couple others got it as well. So that's the scoop ski. So turns out you and I are like incredible chemical factories. We make lots and lots of stuff. And what's interesting too is I read this that the insulin that diabetics have to put in they have to take a lot more of it than like the natural stuff. In other words, the stuff your body makes, the insulin, is much more effective than the human-made stuff in a lab that diabetics have to take. So we're not just chemical factories; we're really good chemical factories. Really efficient. We make lots and lots of enzymes. Some can be used over and over. Some get flushed out with the body as with digestion and stuff. So there are some enzymes that do need to be replaced by the body, okay, because of that. But others that can be used over and over. All right, so they're biological catalysts. Good. So essentially, to wrap things up, we got three ways to increase the speed of a chemical reaction. One, increase the temperature. Two, add more chemicals or increase the concentration. And now three, you can add a catalyst to that reaction. Okay, super. Next time, we're going to talk about two different types of diagrams, or at least one type, see how far we get. Potential and kinetic energy diagrams, and what they have to do with all of this reaction rate stuff. I think you'll like it, and I'll try and plan a day for next week. It depends on my schedule. I need to supervise at the school a bit, but that's pretty good. When are we going to cover polarity this year? No, we'll probably not. Polarity you'll get to, Carlotta, next year. That's my guess. Thanks, everybody, for joining me. Thanks for participating well. If you still haven't said hi, say hi before you go. Other than that, enjoy the rest of your day, and I'll put this online for your classmates. Bye, everybody. Stay healthy.